Okay. Welcome everybody to another MCRN Colloquium. Today we're lucky to have Dr. David Marsico speaking to us. He is a research scientist at CIRES and also works with the NOAA Physical Sciences Laboratory. He got his PhD in 2020 at the University of Wisconsin-Madison, and then I think after that you were at the University of California, Davis. Working in the Department of Mathematics, but also jointly at the Department of Land, Air, and Water Resources. And today he's going to be speaking to us about modal interface drives of the Madden-Julian Oscillation, evolution, and predictability. So with that, please take it away.
Thanks, Christian. So I'll be talking about how modal interference drives Madden-Julian oscillation, evolution, and predictability. So this is a joint work alongside colleagues at CIRES, the Cooperative Institute for Research in the Environmental Sciences, the NOAA Physical Sciences Laboratory, and also the National Weather Service, NWS. Okay. So I'll just start off with a few slides on what the Madden-Julian oscillation is. So the tropics contain phenomena that vary on many different timescales, but in this talk I'll focus mainly on intraseasonal variability. So that's 30 to 90 day timescales, and that's dominated by the Madden-Julian oscillation. So essentially, the Madden-Julian oscillation, or MJO, is an eastward propagating wave that moves at approximately 5 meters per second with a period in the 40 to 60 day range. And it manifests itself most clearly over the Indian Ocean and Central Pacific in the form of this dipole-like pattern of convection, right? So we have what's called enhanced convection. This is where we have strong upward motion over the Indian Ocean. So it's, imagine one large thunderstorm where warm, moist air rises, and then a suppressed convection phase where cold, dry air descends, right? So we have this dipole-like pattern of convection moving eastward. So why is it important? So the MJO is important because its impact can be felt around the world. So I just, included this picture that I pulled off the PSL, the Physical Sciences Laboratory website, showing all of the impacts that the MJO can have across the globe. So it can impact monsoons over India, say, and hurricanes and precipitation over the United States, to name a few. So we obviously want to understand how this thing works. So another form of tropical variability that's very important for the MJO, and we'll focus on in this talk as well, is the El-Nino Southern Oscillation, or ENSO. And this is just a fluctuation in sea surface temperature anomalies, right? SSTs, it oscillates back and forth between the El Nino phase of positive SST anomalies and the La Nina phase of negative SST anomalies. So importantly, the spatial signature, or the spatial pattern of ENSO, actually overlaps with that of the MJO over the Central and Eastern Pacific. And the main goal of this talk will be on how to effectively filter out the ENSO signal from the MJO. Okay, so how do we actually identify the MJO in data? So it's usually, or pretty much almost always, done through EOF analysis. So the idea is that we have a small number of EOFs, usually 2. EOFs are just empirical orthogonal functions. They're the eigenvectors of a covariance matrix. And they're interpreted as fixed spatial patterns and a corresponding pair of time series PC1, which modulates the amplitude of EOF1, and PC2, which modulates the amplitude of EOF2, right? So the MJO is effectively represented as this sort of oscillating oscillating pattern, right? We have a fixed spatial pattern, EOF1, EOF2, theta and lambda would just be the latitude and longitude, and their amplitudes are modulated by PC1 and PC2. So the amplitude is defined as the square root of PC1 squared plus PC2 squared, and EOF1 and EOF2 are orthonormal, right? So they're orthogonal, and they have unit magnitude, right? So the amplitude is just root PC1 squared plus PC2 squared. The phase is just the angle between PC2 and PC1, the angle between the time series. And an MJO event is defined as a time when the amplitude exceeds 1. And so the evolution of the MJO is usually visualized in this phase space, right? We divide the region of the MJO's propagation into 8 different phases, phases 1 through phase 8. Okay, so the particular index I'll focus on here is the most commonly used one, called the real-time multivariate MJO index, or RMM. So it can be constructed by computing the combined EOFs of outgoing long-wave radiation, that's OLR. OLR is used as a proxy for convection. I think it's just easier to measure OLR than it is to measure convection directly. So OLR and upper and lower level, that's 200 and 850 millibar winds in the tropical region, right, between 15 degrees south and north. So a key aspect of this procedure is to remove low frequency variability associated with ENSO by subtracting off the 120-day mean. We can then take observational data, project it onto EOF1 and EOF2, right? The spatial patterns of which are shown here to obtain our indices RMM1 and RMM2, right? So RMM1 and RMM2 give us this sort of the contribution from EOF1 and EOF2. This should say EOF2 here.
Sorry, can I interrupt for a sec, David? So
Yep.
why should OLR be a proxy for?
So I think when you have so negative OLR, so that those correspond to cloudy regions, right? So if you imagine radiation sort of emanating from Earth's surface, it's sort of not gonna it's gonna sort of bounce back from a cloudy region, but for a sort of clear air region, right, for the suppressed convection, it'll pass through, and so that's positive OLR. Yeah, so negative OLR means the enhanced convective phase. Positive OLR is the suppressed convection phase. Yep. Okay. Okay, and it's usually the evolution of the MJO is usually visualized through what's called composites. So here the shading corresponds to OLR, and the vectors are the lower level, form the lower level wind field, right? So you can see the enhanced convection initiating over the Indian Ocean, right? It builds an amplitude, propagates eastward until eventually dying off over the central and eastern Pacific, right? So in the bottom right, we list the number of events in each phase, and each of these panels represents an average of the OLR and lower level wind fields over the total number of events in each phase, right? So this gives us a representation of the average evolution of the MJO. Okay. So one of the problems with this EOF-based approach, like RMM, is that it can struggle to disentangle different tropical modes that overlap in space but evolve on different timescales, like, for instance, the MJO and ENSO. So the main idea here in this work is that we use, instead of a purely statistical approach that just relies on the statistical properties of, say, a covariance matrix, we use a dynamical approach by constructing a linear stochastic model of tropical variability to isolate different dynamical modes of the tropics. And hopefully that'll give us a better way of isolating the MJO from other forms of variability like ENSO. Okay. So what does our linear model of tropical variability look like? So we'll use a linear stochastic ODE system as a simplified model of Earth's tropical atmosphere and ocean. And so here L is a linear operator, and psi is a stochastic forcing that's white in time, but it does have some spatial covariance structure. The eigenvectors of L, the linear operator, correspond to the spatial structure of each mode, right? The spatial patterns, and the real and imaginary components of each eigenvalue tell us the e-folding time. That's how long it takes for a disturbance to decay by a factor of E, and also the frequency of oscillations, right? So if I have a complex eigenvalue corresponds to a damped oscillatory mode of the tropics. So our state vector will include the variables that we need, the sort of minimum number of variables that we need to represent both the MJO and ENSO. So we use OLR and the upper and lower level wind fields. So that'll get us the MJO and it'll allow us to compute RMM, and also sea surface temperatures that will allow us to represent ENSO variability as well. Okay, and of course this system would be discretized on, say, a latitude-longitude mesh, so we'll have a finite discrete set of eigenmodes. So what do they look like? So let's look at this scatter plot here, where I've plotted the eigenvalues of the linear operator L from the previous slide. So the horizontal axis, that's the frequency, right? So that's basically related to the real component. That's the frequency of each mode, right? So the closer to zero you are, the lower the frequency of the mode of oscillation. And on the vertical axis, we have the folding time, right? So again, that's how fast it decays. And we group our modes into 4 subspaces based on the folding time. So the black dots, we refer to those as the fast decaying eigenmodes, right? So on sort of intraseasonal time scales that we're considering here, these decay very, very quickly. So they all have e-folding times of less than 10 days. And then we have 2 modes of intraseasonal, 2 eigenmodes of intraseasonal variability, indicated by the orange dot and blue dot. Those are the MJO slow eigenmode, which has a period of 70 days, and the MJO fast eigenmode, which has a period of 45 days, right? So we refer to it as MJO fast and MJO slow because MJO fast sort of propagates faster than MJO slow, but they're both well within the intraseasonal sort of period of oscillation, right? Between 30 and 90 days. These 2 eigenmodes, MJO fast and MJO slow, are also very robust. This sort of dashed inset here just shows the results of cross-validation. And that's what that's one of the main features that distinguishes them from the fast decaying modes. None of the fast decaying modes are robust. So the idea is that to do this cross-validation, right, to verify that the MJO fast and MJO slow aren't just, consequences of sampling, we recompute eigenmodes from 9 independent cross-validated operators that are estimated from the data with a different 5-year subset removed. So both MJO fast and MJO slow, and this is just a zoomed in portion here, have small eigenvalue clusters indicating that the cross-validation operators all contain 2 eigenmodes with temporal characteristics nearly equivalent to MJO fast and MJO slow. And the average pattern correlation of each of these cross-validation MJO fast and MJO slow eigenmodes with the corresponding eigenmode from the full linear model, right, without omitting any 5-year period is very high, right, 0.96 and 0.99. In contrast, the fast decaying eigenmodes, and these ellipses, these are just the so-called best fit ellipses, more just a visualization tool to help you get a sense of how tightly clustered these eigenvalues are, right? So they're for MJO fast and MJO slow, they're sort of isolated and very tightly clustered, but for the fast decaying modes, they have sort of large overlapping best fit ellipses, right, around each fast decaying mode. And a similar thing happens for ENSO. Sorry, similar to MJO fast and MJO slow. ENSO is our final subspace of eigenmodes, right? So those are the sort of slowly decaying set of eigenmodes, all with e-folding times longer than 4 weeks, and they all project strongly onto sea surface temperatures. Okay, right, so we have 4 subspaces of eigenmodes of our linear model of tropical variability. The focus is mainly going to be on ENSO, the ENSO eigenmodes, and the MJO fast and MJO slow eigenmode. Right, so the idea is that we can essentially use these eigenmodes to filter those RMM-based MJO composite into its contributions from ENSO, MJO fast, and MJO slow. Okay, so what do we get when we do that? Figure's a bit blurry on my screen, but hopefully it looks okay. So let's focus on the top 4 panels first. So basically what I did is to take that RMM composite that I showed a few slides ago and filter it into its contributions from the MJO fast eigenmode, the MJO slow eigenmode, and also the ENSO eigenmode, right? So what this is showing essentially is what robust forms of variability is RMM picking up. So we have the total field, and I've combined phases here just for sort of ease of visualization. So in A, we have the total unfiltered field, and this just shows the eastward propagation of the MJO. And then in columns B and C, we can see that most of the RMM-based MJO propagation is due to MJO fast and MJO slow, with a small but non-negligible contribution from ENSO. And the importance of ENSO can be understood by looking at the corresponding Hofmahler plots. So the idea here is that we take a longitudinal average of each field, and that'll show the eastward or westward propagation, right? So in this case, the eastward propagation. So the impact of ENSO is evident at long lead times, indicated here at 20 days by the horizontal dashed line, right? So we can see that the total, right, the total unfiltered field at, say, 20 days is as much due to ENSO, right? We can see ENSO here with its characteristic standing wave nature, as it is due to a form of intraseasonal variability like MJO fast. And this is not desirable, right? We want to have an index for representing the MJO that does not contain any contribution from ENSO, right? So if you're using RMM as a way to represent the MJO, then at long enough lead times, you're going to be picking up a relatively strong ENSO signal as well. Okay, so let's say we want to get rid of ENSO from the RMM. How would we do this? So we can do this easily by using the eigenmodes of our linear system. So the idea is to simply recompute RMM, but now on the ENSO filtered data, right? So we call this new index RMM star. It's simple. We just take take our observed field of OLR and lower and upper level winds, filter out the contribution from those ENSO eigenmodes, and then recompute RMM on that ENSO filtered data, and we just call that RMM star. Okay, so again, the goal of this is to remove the impact of ENSO on an index meant to represent the MJO. So what do things look like when we do that? So let's say we redo those composites from the previous slide. So again, the top four panels, the shading is OLR, the vector fields are lower level winds. So the total field and MJO fast and MJO slow essentially remain the same, right? We have our total unfiltered field, and then columns B and C show MJO slow. And ENSO has been greatly reduced, right? It's just lacks any spatial coherence. And you can really see the impact of this ENSO removal in the bottom four panels, right? If we again plot the Hofmallers by averaging longitudinally between 15 north and south, again, the total field, MJO fast and MJO slow, all remain essentially the same as what they were for RMM, but the amplitude and spatial coherence of ENSO has been really reduced, right? So using this RMM star index gives a more effective way of removing the ENSO signal, or I guess removing ENSO from the MJO, particularly at long lead times, right? If you again look at 20 days, there's essentially very, very little ENSO contribution to the total field, which is primarily explained by MJO fast and MJO slow. Okay, so now we have an index for the MJO, which we just referred to as RMM star, that can filter out ENSO more effectively than RMM, leaving essentially just MJO fast and MJO slow. So the key to understanding the interaction between these two eigenmodes, MJO fast and MJO slow, is by looking at so-called optimal structures. So we're interested in these spatial structures that maximize deterministic linear growth towards the MJO. So this turns out to be critical for understanding the interaction between MJO fast and MJO slow. Okay, right, so this is computed by simply, we square the RMM star amplitude at time t. So we have some initial state x naught, we propagate it forward in time linearly, and then project onto the RMM star EOFs, right? That's what M star does, and then we square that. Maximizing this quadratic form leads to just a simple eigenvalue problem, which we can solve. Okay, so what happens when we do that? So here we maximize, or we found initial conditions that project or that maximize the RMM star amplitude at 15 days. And then we go into observations and find the points in time where the atmosphere most closely resembles these optimal conditions, and then see how they evolve in time. Okay, so what happens when we do that? It's a bit blurry on my end. I'm not sure what happened, but I hope you can see sort of what's going on with the propagation. So here we have the evolution of each field, and I've omitted ENSO because it's essentially zero. So we have the total field, MJO fast, MJO slow, and then MJO fast plus MJO slow, right? So if we look at MJO fast plus MJO slow and compare it to the total field, we see basically that the evolution of the total field is essentially due entirely to the interference between MJO fast and MJO slow. So physically, what's going on between these two modes is that at early lead times, say 0 days, and I included sort of backward time and forward time, but I'm just going to focus on sort of forward time here. So if we start at day 0, MJO fast and MJO slow are initially out of phase, right? So they're sort of interfering destructively, but as time progresses, MJO slow, which has a shorter e-folding time, dies out, leaving just MJO fast, and that's enough to explain essentially all of the total field's variability at longer lead times, right? So at early lead times, we have this destructive interference between MJO fast and MJO slow, and that's what you need to explain the total field. But as time progresses, MJO slow dies out, leaving just MJO fast, which essentially explains all of the total field at longer lead times. Okay. So let's look at how this modal interference, right, between MJO fast, MJO slow, and ENSO can be related to forecast skill. So here we're going to look at how skillful one of the operational models, the ECMWF's integrated forecasting system, the IFS, is at predicting the MJO, right? So we're going to use the bivariate correlation skill score just to see how skillful it can predict RMM and RMM star here. Okay, so a forecast is said to be skillful as long as this correlation coefficient stays above 0.5, right? Which I've plotted here as this horizontal line. So on the left, this panel is meant to show the impact that ENSO has on the skill of predicting RMM, which we show in the red curve, right? So we know that RMM, right? We used our sort of modal decomposition to show that RMM contains a fairly substantial contribution from ENSO at long lead times. And we see that RMM is skillful up until about 33 days, right? Where the red curve intersects this horizontal black curve. But when we remove ENSO, right? So essentially when we compute RMM star, the skill actually goes down to about 30 days, right? So the RMM star dips below 0.5 at 30 days instead of about 33 days like it does for RMM. So what this suggests is that RMM is actually sort of the skill of RMM is actually a bit inflated due to the contribution from ENSO at longer lead times, right? And you can see that contribution by computing the skill of RMM star, right? So essentially ENSO gives RMM a skill boost of about 3 days. So that's about 10% increase in skill at long lead times. Okay, so what impact do MJO fast and MJO slow have on the skill of RMM star? So we saw from the previous slide that once we do remove ENSO and compute RMM star, the sort of total MJO variability is explained essentially entirely by the interaction between MJO fast and MJO slow. So the idea here in this right panel is that we condition the forecasts on the upper 10% of observational states that project most strongly onto those optimal initial conditions that we computed here, right, by solving this eigenvalue problem. And then conditioning the forecasts on those optimal states, right? So when we look at forecasts initialized from those optimal initial conditions that's shown in the blue curve here, we get a skill boost of about 1 week compared to the forecasts that are initialized at all the other times, right? So this interference between MJO fast and MJO slow is critical for understanding the most skillful RMM star forecasts. Okay, so that's my talk. We have plenty of time for questions, I suppose.
Okay, cool. Thank you, David. That was really interesting. Yeah, we definitely. Well, first, I guess let's thank David. Like the clapping emoji. So thank you. And then yes, we have time for questions. Yeah, Chris, please go ahead.
Okay, me. Yeah. So let's see. Can you go back to the linear stochastic model?
Yep.
So so you said that C, the noise, has spatial structure.
Uh-huh.
And so what is that? And how is that different? So all the stuff you're talking about here is, I mean, all the modes that you kind of associate with that you discussed are all in L, aren't they, or not? Are they
Correct.
C?
They're in L. Yep. Yeah.
So how do you decide on the spatial structure of C?
Yeah. So there's a few ways to do it. So here, first you can estimate L, right, and then you can sort of approximate the left-hand side, approximate the right-hand side, and then see psi, the spatial covariance, can just be determined basically as a residual between dxdt and Lx. Yeah.
Where you're finding dxdt by data.
Correct. Yeah.
Yeah. Okay.
Yeah.
Okay. And I mean, is that what you do, or?
Yeah, that's what I do.
There's several ways to do it. So
you can use you can look at the so-called fluctuation dissipation relationship, right? You can form an ODE for the covariance of Q and then look at that in the steady state. Sometimes there are like problems with that approach. It can lead to sort of negative, sort of ill-formed covariance structure, but either way you could do. Yeah.
So if I think of, I mean, I'm a dynamical systems person, as a lot of us here are, and I think of your e-folding time is something like 1 over the real part of the eigenvalue, right?
Right. Yep.
Right. So the fact that these were larger for ENSO means that they're actually smaller as real parts of eigenvalues. Is that right? So because you had that that nice picture there with the green. So that's actually, they're decaying much slower, right?
That's correct. That's right. Yep.
Yeah, so they're much sort of weaker in some sense as unstable eigenvalues from the NJO ones.
Yeah, so all of these will be so all of the real parts, so all of them are going to be stable. And in the absence of the noise forcing, yeah. In the absence of noise forcing, it would just be boring. Everything would just decay to zero, but the sort of noise forcing continually excites them. Yeah.
Right. So that's, I guess, one thing I don't understand. And as you know, I used to listen to Cecile and Prashant, as I indicated in the beginning. I knew them, right? And that all talk about linear stochastic models and how you can go a long way with this. And I always never quite understood why, one's not the stochastic models. It seems that the stochastic part seems like you kind of an afterthought in a way, but it seems critical to keeping the system going. So why isn't its structure part of the modeling?
So also, which I didn't really touch upon in this talk, was, I guess, the sort of non-orthogonality of the eigenmodes of L, right? So were these eigenvector, right? So none of these eigenvectors are orthogonal. If they were, right, everything would just sort of decay, but they're not. So these different eigenmodes can interfere in a way that gives you sort of transient anomaly growth that wouldn't be possible, say, if L was, say, a symmetric matrix. So you have this non-normal interaction between the eigenmodes of L that can give rise to these observed patterns, right? That I showed in observations, and that's actually the key. That I would say that's probably more important than the stochastic forcing.
The stochastic forcing just keeps that alive.
Yeah, the stochastic forcing will often do sort of long climate runs, right? We can, generate synthetic data sets from this simple dxdt equals Lx plus psi. And the stochastic forcing is very important there to, as you say, keep the system alive. And also the stochastic forcing, again, I didn't really touch upon this in this talk. If you actually look at, instead of looking at the eigenmodes of L, the linear operator, if you look at the eigenmodes of the sort of spatial covariance, the covariance matrix of psi, those gives you the structures that are most sort of effectively excited by noise forcing. So noise forcing itself, again, which I didn't really talk about in this talk, can give rise to certain observed patterns, and that's sort of what I'm working on now, going in more detail into the structures, right? So here I looked at the deterministic, right? I think in one of my right. We want to look at optimal structures that maximize deterministic linear growth towards the set of spatial patterns that describe the MJO. You could also look at the set of spatial patterns that are sort of most efficiently excited by noise forcing as well.
Okay. Thanks.
Yep.
Any other questions? Okay. So yeah, thank you again, David, for a really interesting talk.
Thanks.
Oh, sorry, I thought I heard a
question. Yeah, I thought.
Sorry, I just said thank you.
Oh, thanks. Yeah.
Well, yeah, so thank you very much. And so let's all thank David again. I always love to click the clapping emojis. And yeah, unless there's any other questions. Perfect. Okay. All right. Thanks, everybody, and look forward to seeing you next time.
Thanks. Yeah.
Thanks.